Okay, starting the cluster analysis, we're going to look at using Kmeans clustering technique in our cluster analysis. And the first thing that we do is we don't want to use all of the features in our cluster analysis to make it kind of unbiased as possible. I'm not including legendary or generation or even the total power. We're going to look at the individual stats, HP, attack, defense, special attack, and special defense, and see what groups we find by clustering with those, just those techniques. So not the type of Pokemon or anything along those lines. So it's a little bit trying to be as unbiased as possible and just looking at the raw stats of each Pokemon. We're going to start by looking with the means distribution, or mean distortions, and this is used in the elbow method. So what we'll be doing, just like your elbow, we're looking for an inflection point where this distribution plots. So what I've done here is listing, we're going to look at Kmeans of 1 to 49. Remember, this is Python, so the last number is always exclusive. And we're going to loop through the range of 1 to 49. And we're looking at plotting the clusters, we're fitting the clusters, we're going to predict, and then we're going to use mean distortions. And then what we're going to do is we're going to do a line plot, a simple Seaborn SNS line plot to look at the mean distortions by cluster. And what we can see here, there is no real elbow point or elbow method. It doesn't work with this. Really, and this is very insightful because it seems like every Pokemon really is truly unique. There isn't a good grouping. We can look at going up to 300 and this pattern continues. There really is no inflection going up to the maximum amount that we can go. I only run 50 here to save time for our analysis at this point. But so attempting to use the elbow method did not reveal evidence of an inflection point, and therefore we can't use the elbow method technique to determine clusters. But this also gives us the hint that every Pokemon is in fact unique, which I find very interesting. After 5 generations, 6 generations of Pokemon, and they're still coming out unique, which is really quite interesting. The next thing we're going to look at is the silhouette scores. So sil score, just finding an empty list, cluster list, and we're going to look at clusters from 2 to 13, and we're going to loop through those. And we're doing the K-means for each of the clusters that we're looping through, and we're fitting and predicting, and we're going to look at the silhouette scores of those final predictions in comparison to our original clusters. So here what we find is this is much more insightful. We find that a silhouette score of 6, this grouping is even better than 5 or 4, and it drops really kind of off a cliff after 6. So we chose in our analysis to look at 6. But just looking kind of on either side of that to really determine what those would look like, we're going to use Silhouette Visualizer. We put a K-means of 7 inside of that, and we're going to look, and then a really important thing we're using Yellow Brick Road is we always have to fit the graphic. After you call and assign it to a variable, we're going to fit the graphic, again, using just the clusters that we would determine. And looking at 7, it has good separation, but we can see here there's quite a large negative number for this one, or for the silhouette score of this one type. Here what we can see is this looking at the 6, which we'll be using for our analysis later on. It gives us really good separation. All of them are they reach up quite a large amount above the average silhouette score, and we don't have too much. All of these have very little negative silhouette scores, so there isn't a lot of overlap in our clusters, which is really good to determine. And if we look at 5, you can see 5 might be better, but it's good to go with the highest number of clusters that makes sense. So we do see here that there is a good grouping here, and there's very little negative score, especially in this group right here in the red. We don't see that the cluster really has a negative silhouette score. So another way to kind of confirm that 6 is a good amount is we're going to look at the intercluster distance. So if we clusters of 6, and let's plot that. So we're going to look at the K-means of 6, and then we're going to use the intercluster distance from Yellow Brick Road to look at the distance. And we can see here we have very good separation. There's a little bit of overlap, but we still see really good separation between all of the groups. And this is actually really quite good because normally we would expect to see some overlap, and that's fine. But here we actually see really good separation on all of the areas. The next thing we do is we assign those labels back into the data frame for our analysis. And I'm going to end up saving these just so that we can use them in our analysis. So feature cluster, and we're going to append the name as well. So we're adding this to our feature clusters, the list of the features that we use in the cluster. So appending that, and then we're going to group by the new name that the new spot in the cluster we've assigned. So the new grouping of the clusters, and we're going to look at the mean. And then what we're going to do is put back in another group by object that's just looking at the count of each variable. So we do one group by object, and we're assigning that k plus k profile, k means. And then in the k-means, we're going to add one more column of the cluster count. So we're looking at the means, and then we're going to add the count. Very, very handy technique. So the one thing is that we are not able to do, when you do clustering, we did set the random state to be 42. So it's going to be the same time every time, but the way that it assigns, the label that it assigns to each cluster is still going to be random. So it's a good practice to actually save your data frame with one thing, and then we're going to use these again in our analysis. So we save df to CSV, and I've saved this already, and I'm going to pull up the file that I've saved, and I'm going to save this as df cluster. So this is the same data frame as the original, and adding into that with our cluster analysis with the saved clusters, just so we're not changing the labels. And because we're going to change those names and use those as reference points, it's good that they don't change. So here we're just appending some of the other features we didn't look at in our cluster analysis. So total generation legendary. And then we're going to use the group by object where we assigned the count to each one. So feature clust, group by mean clust, and we're going to look at the mean, and we're going to highlight the maximum of each of them. So if we group by the clusters, we're going to assign by the mean, and we can see here that if we look at cluster 0, it's very, very weak. They really don't have very good scores at any point across the board and very low total scores. We can see that number 1, remember that we didn't put in legendary, but all the half of the legendaries got grouped into this, and some other very strong Pokemon. So I'm going to call this, is when we see this later, these are legendary-like Pokemon. We can see here that there's a very strong defense in the third grouping, group number 2. And here we have kind of a mediocre group, a group that has generally good stats across the board, but nothing really phenomenal either. Kind of generally good across the board. In the fourth cluster, or cluster number 4, we have a really strong special defense and special attack, but really generally good stats, but really strong special attack and special defense. And then we have, in the last cluster, we have generally high scores with a very strong attack. So this is a good kind of go-to grouping for Pokemon. We just want to look at the median as well and make sure that the mean isn't being pulled by outliers. And we see the same pattern as we do above with the median. And this is just to confirm that, again, the outliers aren't having any effect on our groupings. So I ended up naming, this is why we ended up saving this, so that we can name our clusters. And I'm going to call cluster 0 the weaklings, cluster 1 legendary like, cluster 2 stonewall, and that's because they have a strong defense by a large margin compared to the other Pokemon. In cluster 3, I'm going to call ordinaries. These are kind of mediocre across the board. Cluster number 4 is the hidden surprises, and cluster number 5 is the strong. I'm going to call them strong. They have medium high attack with our medium high across the board with high attack. So kind of your go-to Pokemon. Here I'm going to change the name. I'm going to use the replace function from pandas to replace the cluster names or the cluster ID numbers with the cluster names that I just listed up above. And so we do that. And here we can see we have roughly about 246 weaklings, 147 ordinary, 119 hidden surprises, 110 strong, 78 legendary like, and 55 stonewall.